Hello everyone, my name is Alejandro Jimenez Rios and my presentation is about the experimental campaign on the use of the flatjack test in cop walls that I performed during my PhD at the Department of Civil, Structural and Environmental Engineering at Trinity College Dublin in Ireland. The flatjack test is one of the most used investigation techniques in the area of architectural heritage conservation. Unfortunately, as far as we knew 3 years ago when this experimental campaign started to be planned, there were no results available in the literature reporting the use of the flatjack technique in cove walls. It is well known that prior to the application of a new experimental test in an existing building with historical value, it is necessary to validate its feasibility by the means of an experimental campaign. This presentation is concerned with the first experimental campaign performed to validate the use of this minor destructive technique to determine the levels of stress in cove walls and their mechanical properties. This will be the outline of my presentation in accordance to the template provided by the conference organizers. I will start with the motivation, then I will present the methodology. I will continue with the results and the discussions, and finally, I will conclude with the conclusions of future work. Cove is an earthen construction technique that was traditionally used in at least 18 European countries and many others around the world to build mainly dwellings and farming buildings. In 2012, UNESCO created an inventory of the World Heritage Earthen Architecture. The inventory identified the presence of earth materials in 150 sites, part of the World Heritage List, among which 29 sites contained cove elements. Just to mention a few, we can highlight the royal palaces of Abu May in Benin, Africa, the city of Sana'a in Yemen, and the historical monuments of Nara, Japan, both in the Asian continent, the historic Cité of Lyon in France, Europe, and in America, the archaeological site of Paquimé in Casas Grandes, Mexico. The flatjack test is one of the most applied investigation techniques in the field of cultural heritage conservation. The purpose of this experimental campaign was to assess the feasibility of the technique to measure the average compressive stress levels in existing cove walls and determine their mechanical properties. With the data obtained from the single flatjack test, it is possible to estimate the level of stress at which the wall is being subjected at a particular location. With the data obtained from the double flatjack test, the values for Young's modulus, Poisson's ratio, and compressive strength of material can be estimated as well. This experimental campaign started with a literature research process that helped identify key aspects for its execution. A research collaboration was established with the University of Cantabria in Santander, Spain, in which advice and paramount information was provided by Professor Ignacio Lombillo, who previously had performed flatjack tests on adobe and ramter walls. Then, I learned the traditional cove construction technique during my participation at the Base Habitat Summer School that was organized by the Department of Architecture at the University of Linz in Austria. The material required for the construction of the wallets was locally sourced around the Dublin area. 6 wallets were built on top of steel pallets to facilitate their movement around the lab. The soil used was tested both qualitatively and quantitatively, and its index properties were determined. The mixing of all constituent materials, namely soil, water, and straw, was done manually following the Irish tradition, and with the mix, the wallets and 6 cylinders were prepared. The cylinders were tested under simple compression to estimate the compressive strength of cove. The wallets were capped with a mix of cement mortar to flatten their top surface and achieve a regular load distribution, and were left in the lab, protected from wind and rain during a drying period of 3 months. The wallets were then consolidated as advised by Professor Lombillo under 2 load cycles. From the second load cycle, which resulted in a linear behavior from the wallets, Cobb's Young's modulus was estimated. After the consolidation of the wallets, we proceed to perform the flatjack test on them in accordance with RILEM and ASTM standards. for the application of the flat jack test on masonry walls and with slight modifications for their applications on cob wallets. The index properties of the used soil are summarized in this table. The soil was identified as an anthropogenic reconstituted soil without reworked natural materials. Furthermore, the soil was also classified as CIM, medium clay, as a very stiff clay, and as well as a well-graded soil. In this figure, it can be seen that the particle size distribution of the soil perfectly fits within the upper and lower bounds recommended by the reference authors for the construction of cob walls, which represent the necessary amount of clay content in order to achieve the bonding of bigger particles and provide the cob wall with cohesion. 6 cob cylinders were prepared using random samples of cob mix prepared for the construction of the wallets. The cylinders had dimensions of 15 centimeters diameter and 30 centimeters length. They were left in the lab during a trying period of 3 months, during which their size and weight was controlled to estimate shrinkage and density. The average cob cylinder's compressive strength was 0.697 megapascals, with a standard deviation of 0.083 megapascals. The compressive strength value obtained was very similar to that reported by Pullen and Schultz of 0.703 megapascals. This data gave us a point of reference to establish the consolidation and test loads to be applied to the wallets. Here is the consolidation setup used on the cob wallets. The load was applied by pre-stressing the rough steel bars located 2 at each side of the steel pallets. The load applied to every bar was measured with a load cell, and the deformation of the wallet was measured with 4 LVDTs located 2 at each face of the wallet at their middle third of the height. As it can be seen in the figure, all wallets presented a nonlinear stress-strain relationship during the first consolidation load cycle. The cause of the nonlinearity was not the load level, as it never exceeded a maximum value of 85 kilonewtons, which induced a compressive stress of only 0.21 megapascals in an idealized cross-section of 0.4 square meters. This value represented only 30% of the compressive strength obtained from the cob cylinders. The full consolidation of a soil is only achieved after a relatively long period of time, hundreds or thousands of years even. For practical reasons, though, it was accepted that for this experimental campaign, the level of consolidation will be such that further deformations caused during the time period of the performance of the flat jack test will be negligible. For example, when the displacement increment due to the cob consolidation were less than 1%. To achieve this, the load used for consolidation, roughly 85 kilonewtons, will be bigger than the load at which flat jack test will be performed, approximately 50 kilonewtons. As can be seen in this second figure, which represents the average displacement measured with the LVDTs under a constant load over time, the increase in average displacement between the fifth and the sixth state of consolidation, roughly between 6,000 and 7,000 minutes, for all wallets was practically null in comparison with the average displacement recorded during the first hours of the consolidation process, from minute 0 up to roughly 300 minutes, when displacement increments of up to 80% were observed. The last figure in this slide presents the linear behavior obtained after a second consolidation cycle. The mean Young's modulus value obtained was of 143.3 megapascals, with a standard deviation of 32.6 megapascals. In this figure, the average deformation recovery curves obtained from the single flat jack test performed in the 6 cob wallets are shown. It can be observed that as the pressure increased in the flat jack, the average deformation of the control points, originally caused by the release of stresses when the cut was made, decreased as expected. The recovery pressure of every wallet was computed as the linear interpolation between the 2 pressure points that presented the last positive and first negative average deformation value respectively. The mean recovery pressure was of 0.345 megapascal with a standard deviation of 0.0327 megapascals. After applying a series of coefficients related to the area of the cut in the wall and to the manufacturing of the flat jacks, a mean value for the dimensionless geometrical efficiency constant was obtained as 0.48 with a standard deviation of 0.0427. This figure presents a summary of the stress-strain curves obtained from the double flat jack test. The positive values of strain represent a decrease of the distance between control points, whereas the negative values of strain represent a separation between the control points. Therefore, the stress-strain curves plotted to the right of the zero value correspond to the strains of the vertical control points, and those plotted to the left correspond to the horizontal control points. The values obtained for the mechanical parameters of cove wallets are the ones shown in this table. Here we can also see the reference value obtained from the compressive test of the cove cylinders and Young's modulus obtained from the consolidation process of the wallets. The Young's modulus of the material, estimated by taking into account the slope of this last elastic range on the stress-strain curves, was in good agreement with the value obtained from the slope of the consolidation process stress-strain curves. As highlighted by the t-test, no statistically significant difference was observed between the mean value of both groups. On the other hand, the second Young's modulus value, obtained with equation 26 in accordance with Rilem MDTD5 and corrected by using a value of key A of 0.51, resulted to be roughly 50% less than the value obtained from the slopes of the stress-strain curves. Therefore, it is advised not to correct the values obtained from the stress-strain ratio as per specified in ASTM-C 1197. The uncorrected values give a more accurate estimation of Cobb's Young's modulus. Regarding the failure patterns observed after the completion of the double flat jack test, it could be said that the presence of a consistent pattern in the form of a series of vertical cracks, mainly concentrated at the center of the material between the two horizontal flat jacks, was identified. This set of vertical cracks located at the center is more similar to the typical vertical crack pattern that appears in compression tests under point load, such as in the Brazilian test, than to a typical X-crack pattern characteristic of a simple compression test. This is in agreement with the assumption that the non-uniform deformation of the flat jack transmits a more similar point load than to a uniformly distributed load to the material. A detailed study on the distribution of the stresses induced by the flat jack to the fabric, performed by Hughes and Picard, showed that effectively the pressure was higher at the center of the flat jack than at its edges. This phenomena is amplified in cove walls, and therefore the value obtained for the dimensionless coefficient Ke is smaller than the values of Ke for other wall typologies, for example 0.9 for adobe walls and 0.82 for rammed walls, as reported by Lumbillo. This can be justified by the fact that cob is relatively weak and flexible in comparison with other materials, namely adobe or rammed earth, as shown by Micoli et al., and stone or brick masonry, as shown by other authors. As a consequence, when the pressure in the flat jack is increased, it deforms more like a balloon than like two parallel plates being perpendicularly separated. As can be observed in the sketches of this figure, which presents the original distance between control points Di being recovered, the deformation at the flat jack centroid in the cove wall figure A is relatively big in comparison to the deformation suffered at its edges, whereas that the flat jack's deformation in the masonry wall, figure B, is more uniform. It is worth noting that the strain values of the curves observed in slide 10 for the results of the double flat jack test are counterintuitive. As pressure was applied vertically to the material between the flat jacks, it was expected to see larger vertical strains caused by the actual compression of the material than horizontal strains caused mainly by lateral deformation of the material due to Poisson's effect. Nevertheless, after apparently yielding point of what was reached, the increments of horizontal strains was relatively larger in comparison to the increments of vertical strains. This phenomena may be better understood if the relatively high stiffness of the flat jacks in comparison with that of cob is taken into account. When the pressure is increased by pumping oil in the system, the flat jacks start to deform. The deformation is not uniform separation of the stainless steel plates, but more like a balloon inflation with bigger deformation at the center of the flat jack and practically negligible along its edges. The effect of this differential deformation is practically non-existent for small deformations, but becomes significant as deformations grow beyond the yielding point of the material, which actually happened while performing the double flat jack test of the cob wallets during this experimental campaign. The uneven deformation of the flat jacks caused that the pressure got transferred to the wallets in a non-uniform way. The actual load transfer to the wallets was more similar to a point load than to a uniformly distributed load. Furthermore, the almost zero deformation of the flat jacks along their edges, namely at the wallet's faces, does not cause any restriction to the bulging of the material, as can be seen in Part A of this schematic figure. Therefore, bulging compensates some of the vertical deformation caused by the increment of the pressure, whereas that, at the same time, contributes to the further increment of the horizontal deformation of the material caused by Poisson's effect as depicted in Part B of this figure. From this experimental campaign, it could be concluded that both single and double flat jack tests were performed successfully, that it was determined that the single flat jack test tended to overestimate the average value of stress by a factor of 2. Therefore, it is advised to apply a value of Ke of 0.51 to correct the average compressive stress values obtained. And finally, that the mechanical properties determined with the application of the double flat jack test can be used to define material constitutive models and integrate them into a structural analysis to reproduce cob structural behavior. Thank you for your attention.